This conference will now be recorded.
Hello everyone. Today we are going to discuss previous year's questions, and that is from the unit chemical bonding and molecular structure. So this is inorganic chemistry. And all these questions are from the exam JEE Main. So here we have question 2024, and this is statement 1 and statement 2. Two statements are there and options are related to these two statements. The first statement is saying that a pi bonding molecular orbital has lower electron density above and below the internuclear axis. Sorry, there is a spelling mistake. So this statement is related to pi bonding molecular orbital, and it is saying that there is lower electron density above the internuclear axis and below the internuclear axis. Internuclear axis means when we have pi bond between two atoms, then suppose we have pi bond between atom A and atom B. So these are the pi orbitals, right? So this will be the internuclear axis, and it is saying that there is low electron density above this axis, below this axis. So is it true or not, that we have to find. Come to the next statement. It is about pi star anti-bonding. So the previous one is related to bonding pi, and now it is anti-bonding pi. That is what is pi star. And this statement is saying that pi bonding anti-bonding MO, pi star anti-bonding MO, there is a node between the nuclei. So this is nuclei 1, this is nuclei number 2. Is there a node between the two nuclei? That is the question. So we have to see a proper picture related to pi bonding and pi star anti-bonding so that we can understand whether these statements are correct or not. So here you can see in this picture, the first one is basically for pi and the second one is for pi star. You can see same phase sign on the same side, plus plus minus minus. And suppose this is py orbital. Just for example, you can also take px or pz, it doesn't matter. So there is same phase sidewise overlap, and electron density is very high above the internuclear axis and below the internuclear axis, right? So the first statement cannot be correct. So the first statement we can say this is false based on the first picture. Now the second picture, as it is pi star, sorry, it will be negative, it will be positive. The first picture is okay. Now as this positive sign and negative sign of this phase, it is not matching, now there will be a node. And this electron density, as you can see, they are as if shifted away from each other, right? So there is a nodal plane present here, and another nodal plane is already there, because you can see electron density is minimum at these positions. So two nodal planes are there, but it is talking about the node which is between the nuclei. So this is the node which is between two nuclei, nuclei number 1, nuclei number 2. There is another nuclei, that is fine. But in between these two, there is also a node, two nodes, but one of the node is fulfilling these criteria, right? So that is why here first statement is not correct, but second statement is basically correct. So it is F and T. Statement 1 is false, and statement 2 is correct. Option 3, correct option. We'll go to the next question. Arrange the bonds in order of increasing ionic character in the molecules. Here we have total 5 molecules. Lithium fluoride, K2O, N2, SO2, ClF. 3. Increasing ionic character. That means, just take the first example. Here N2 is at the left hand side position and LiF, it is at the highest position. That means LiF is having maximum ionic character and this is having minimum ionic character. Now this is minimum ionic character means here covalent character will be maximum at the left hand side terminal. Okay. Now when we take decision whether it is ionic character or covalent character, you just have to understand the electronegativity difference. Suppose we have bond between A and B. Now this bond, whether it will be covalent or not, that depends on the electronegativity difference. Suppose A and B, their electronegativity are very close to each other. And it is very much true for similar type of atoms. Suppose bond between same atoms, BB or AA, there is no electronegativity difference. So obviously it will be covalent, right? But when electronegativity difference is very high, the chance is that anionic character will also be very high. Now here among these 5 molecules, the nitrogen is the only molecule where both the atoms are same. So obviously there will be least anionic character. So you can place nitrogen at the least position. And if you do so, these two options are already cancelled. Now you are stuck between the first option and the second option. Now here if we think about electronegativity difference, then come to the molecule LiF. We know Li is from S block and fluorine it is from the right hand side part of the periodic table. It is highly non-metallic. So there is obviously huge electronegativity difference. Then if you consider ClF3. Now Cl is some, that is Cl and F, both are actually towards right hand side of the periodic table. So there will not be much difference because it is bond between two non-metals. But lithium and fluoride bond between two, one metal, one non-metal. So LiF should have maximum ionic character, because if you even consider K2O, it is true that potassium is also metal from the left hand side, S block. Oxygen is also very electronegative, but fluorine is very much electronegative. So this electronegativity difference, it will be maximum. So that is why LiF we should keep at first position. But that is also same for option 1 and option 4, because in these two we have already cancelled. We are now stuck between 1 and 4. So we have to focus on these 3. Now among these 3, next if we consider sulfur and oxygen. Now sulfur and oxygen both are actually towards the right hand side, right? Now among these 3, that is what I am trying to say, ClF bond, I am just considering there is a single bond, though all are not single bond, then SO bond and then KO bond. Now among these 3, in which case maximum electronegativity difference is there? Obviously KO. So that is why after LiF it should be K2O, but that is also present in both the options. Now we are stuck between these two. Now in ClF3, if you see the electronegativity difference and the difference between S and O, both are actually similar because both are non-metal. Cl and F both are from same group, 17. Sulfur, oxygen, they are also from the same group. Then how we will decide? Now how we will decide? The answer is you have to consider oxidation state. So when it is SO2, sulfur is having double bonds two sides, so it has higher oxidation state. But if you consider ClF3, there is 3 single bond, 3 ClF bond. So oxidation state, if you consider, for oxygen it is -2, for sulfur it is +4. Here for fluorine it is -1, for Cl it is +3, because fluorine is more electronegative, so we should consider negative charge over fluorine. So oxidation state, both positive and negative, if we see, in this case it is +4 and -2, but here it is +3 and -1. So more higher is the oxidation state over cation and anion, more will be the chance that it will have covalent character, because ionic character is always associated with lower oxidation state and covalent character is associated with higher oxidation state. So in this way we can choose between SO2 and ClF3. As in ClF3 there is lower oxidation state. ClF3 lower oxidation state, so it will have more ionic character. That means ClF3 should come before SO2, and this option is the correct option. So here we have this explanation. Just have a look. The ionic character in a molecule dependent upon the electronegative difference between the constituent atoms. The greater the difference, greater will be ionic character. So based on this logic, we can easily cancel the third option and the second option. But when you are choosing between option 1 and 4, you have to consider the oxidation state. So lower oxidation state and higher oxidation state. So in this character, ionic character is high, and this is associated with more covalent. So that is why we are choosing ClF3 before SO2. So this option will be the correct option. Fine. Linear combination of atomic orbitals to form molecular orbitals takes place only when the combining atomic orbitals, which of these properties should be present. We have A, B, C, D, and you have to choose the most appropriate from the options given below. So in the options, it may be that is either 2 or 3 of A, B, C, D are present, right? So when we have molecular orbital formation starting from atomic orbital, there must be some criteria that should be fulfilled. Otherwise, it cannot form molecular orbital. It is not that you can take any atomic orbital and you are simply combining it and you are getting some MO. There must be some special criteria present in these two AO, that is atomic orbital. Then only it can form some MO. Now, what is those characters? The first one is saying have same energy, minimum overlap. Now, minimum overlap is not possible because two atomic orbitals, when there is very intense overlap, then only the MO will be very strong, right? So minimum overlap cannot be correct. Then the third one is saying same symmetry about the molecular axis, and the last one is saying different symmetry about the molecular axis. Now see here, B cannot be true even if you have doubt related to ACD. But one thing is sure, minimum overlap cannot be a good a criteria for MO formation, right? So in any of these options 1, 2, 3, 4, you can easily cancel those where you have the presence of B, because that is not correct. Here we have B, not possible. B, not possible. B, not possible. So now you can choose option 2. A and C, just based on the fact, if you know that B is wrong, that is enough to choose it. So A and C is actually correct. Different symmetry. Basically, C and D cannot be correct together. Same symmetry about the molecular axis. That is actually the right one. And if it is true, D cannot be true. C and D simultaneously cannot be true. Either one of them should be true. And it is the same symmetry. And similar type of energy, even if it is not exactly same energy, it should be close to each other. Suppose one atomic orbital is having very high energy, another atomic orbital is having very low energy, then MO formation will be difficult. They should be having same energy or energy very close to each other. These are the criteria, not B and D, but A and C. Here also we have two statements and we have to choose whether they are false or not. Here options are always given like this, that is TF, then FF, this one is TT. So all the possible combinations are there. These statements are related to NH3 and NF3, these two molecules. It is saying that since fluorine is more electronegative than nitrogen, it is true that fluorine is more electron, that we know. The net dipole moment of NF3 is greater than that of NH3. So it is saying that because of this fact that F is more electronegative than N, overall dipole moment of the molecule NF3 greater than overall NH3. But is it the criteria based on which we can decide the net dipole moment of a particular molecule? No. You have to draw the molecule and you have to check the individual portion of the molecule. That is, how many bonds are there, whether there is a lone pair, what is the electronegativity difference between the two atoms. Everything we should consider. Then only we can decide whether it will have more dipole moment than the other molecule. So just this fact that F is more electronegative than N. So these two molecules, N is fixed, just 3 fluorine is replaced by H. And as we are saying that F is more electronegative, so overall NF3 will be more. No, you have to check the electronegativity difference between NF and NH. And if in the molecule there is some lone pair, that also you have to check. Fine. So this is the first statement. Now come before the second statement, which is saying that orbital dipole due to lone pair and dipole moment of NH bonds in opposite direction. Now to understand this, obviously we have to know the picture. So this is the two molecules NF3, NH3. Now nitrogen is more electronegative than H. So if you look at the individual NH bonds, the direction of dipole moments will be towards nitrogen. Okay, and whenever there is lone pair, the direction is towards lone pair. Now that is common for both. So here also from N to L, Here also from N to N, that is fixed. But here N is more electronegative than H. But in the second one, F is more electronegative than N. So obviously now the directions will be towards fluorine, not towards nitrogen. So overall what is happening? This direction is towards lone pair and all these three directions are towards nitrogen. As a result, the resultant dipole moment, that's the overall net dipole moment, which is indicated by this pink colored arrow, that is basically downward for NF3. This is downward overall, but for NH3, all the directions of individual dipole moment directions, they are towards the same side. So overall direction is like this. So all are reinforcing each other, isn't it? But for in NF3, it is not so. Directions are different. So that is the reason we cannot say statement 1 is correct. That is net dipole moment of NF3 is greater than NH3. No, that is not correct. Come to the second statement. Is it correct? It is saying that in ammonia, orbital dipole due to lone pair and the dipole moment for NH bonds, they are in opposite direction. No, they are not in opposite direction, that we have already seen. Let me resolve. So here, look at the molecule NH3. All the direction are towards same side. Just consider the red arrows. All the direction are towards same side, not opposite side. This is wrong. And it is saying that in NF3, all are in same direction. Basically, these two, if you reverse, then it will be true. But statement 2 is not correct. Both are false. Fine. The molecular ion with square pyramidal shape. Now, chemical bonding molecular structure in this chapter, we do not talk about the bonding for D block metal complexes. That is basically from the chapter that is D block related chapter, not from here. Because the rules that we apply when we decide any geometry or shape of molecule, that is not from D block. It is mainly for P block. For example, if you consider these three, you can apply the rule that we learned in this chapter. But for this molecule, those rules are not directly applicable. Here, different theories are there. But still, this is a combination question, and we have to understand whether it is square pyramidal or not. So, without going into the details for the D block metal complexes, why they are having different type of shape. Basically, here you can see coordination number is 4. So for D block metal complexes, when coordination number is 4, two possibilities are there. Either it is tetrahedral or square planar. And for nickel CN, it is basically square planar. Nickel is having +2 oxidation state and 4 negative charges are coming from 4 cyanide. So overall negative charge will be 2 negative, extra 2 negative charge. So this is square planar and it is not the correct option. And when it is 6 coordination number, mostly it is octahedral, right? Now come to 2, 3, 4. Here the rule that we'll apply, we have to know the steric number. Now steric number is half of total valence electron. Then M, capital M is, this rule I have already discussed in the respective chapter, that is chemical bonding molecular structure. You can also check that particular class. But here I will just show the rule. Total valence electrons for the central atom, total number of monovalent atoms attached, which is capital M, and plus minus C. C means if it is positive charge, you have to subtract it. If the molecule is overall having some negative charge, you have to add it. But in these three molecules, all are neutral, so we don't have to consider C. Now for PCl5, phosphorus is the central atom. So for phosphorus, if we consider the steric number, valence electron is total 5 because it is from group 15, and group 15 means the last digit is basically the valence electron. Number of monovalent atoms attached. So phosphorus chlorine is monovalent atom here. There is single bond between P and Cl, not double bond. So that is why it will be 5 and this part is 0. So 5 plus 5, it is 2, we are getting 5. So when steric number is 5, it will have trigonal bipyramidal structure. So it is not square pyramidal. Fine. And the same is also applicable for PF5 because the calculation will be same. Now what about BF5? BRF5. For BRF5, again for BR is from group 17. That means 7 will be the valence electron. Number of monovalent atoms attached 5. This part is 0. So now it will be 6. Now 6 means what? Steric number 6, octahedral geometry. But see, though we are saying octahedral, but total bonds are 5. There will be a lone pair in these positions. So without the lone pair, if you consider the remaining shape, it is actually square pyramidal. But for PCl5, PX and PF5, in general, if I consider the formula PX5, it is like this. Triagonal bipyramid. But BRF5 should be the correct answer. Fine. Choose the correct option. Here we have column 1 and column 2. BRF5, H2O, ClF3, SF4. So one molecule we have just solved. So obviously BRF5 is square planar. So A is matching with 4 and that you can have in option 1 and option 2. So these two you can cancel based on this fact. Now come to H2O molecule. For H2O, the central atom is oxygen and oxygen is from group 16. So 6 will be its valence electron. So steric number if we calculate, it is 6 number of monovalent atoms attached to and plus minus 0. So what you are getting 8 by 2 you are getting 4. So when steric number is 4, it is basically tetrahedral. That is the overall shape. But as with oxygen there is 2 hydrogen. So rest of the positions in octahedral that will be 2 lone pair. So without the lone pair if you consider the shape, it is actually bent. So B should be matching with 3. It is bent structure. Just focus on this part. Isn't it bent structure like this? Now come to ClF3. Now ClF3 steric number for chlorine it is 7. 3 monovalent atoms attached. So it should be 5. Now 5 means it is TBP geometry. But see, in TBP geometry, we do not have total 5 fluorine. We just have 3 fluorine. So rest of the 2 positions, lone pairs are always in the equatorial position. So without the lone pair, if you consider the rest of the shape, it is like this. So this type of shape, it should be T shape. Okay. So C should be matching with 2. And what about the last one? CF4. Sorry, SF4. So for SF4, sulfur is from group 16. So its valence electron should be 6. Number of monovalent atoms 4. 6 plus 4, 10. So it is 5. So again we will have TBP geometry. So there also another. Now the shape is like this, isn't it? And this type of shape is known as seesaw. So this is T shape. Very easily you can understand. And this type of shape is known as seesaw. So it should be matching with 1. D is 1, C is 2. Assertion reason type of question. There is considerable increase in covalent radius when we are moving from nitrogen to phosphorus. That is, we are talking about group 15. However, from arsenic to bismuth, only a small increase in covalent radius is observed. So, group 15, first nitrogen, then phosphorus, then arsenic, then antimony, then bismuth. So, it is saying, as we know, when we move down, there is increase in size. But how the size is increasing? Is it very drastic increase or small increase? That is the thing it is mentioned here. So it is saying that there is very large increase, that is considerable increase when you are moving from N to P. But when you are moving from S to SB, SB to Bi, the increase is not so high. Reason is saying that covalent and ionic radii in a particular oxidation state, particular because no oxidation state is mentioned in assertion. So when oxidation state is common, then the covalent radii or ionic radii increases down the group. Now individually if you see, reason R is basically correct. That we know. In any group, when you move down, there is increase in size, provided oxidation state you have fixed it. And it has to be, because when you are moving down, extra valence shell is added. So this is actually true, but is it the explanation for the previous observation? And also, is the previous observation that is mentioned here, is it correct? Yes, it is correct. Basically, it is the fact. Statement 1 is fact. Observe fact. If you simply consider its size, you will see the size is basically increasing. But here from this table, that is, which is electronic configuration, you will know the actual reason. Statement 2 is true, but it is not the correct reason. The actual correct reason is, it is because of presence of completely filled d and f orbitals when you are talking about the heavier elements. So for heavier elements, that is up to phosphorus, there is no presence of d electron, but when it is arsenic, antimony, bismuth, you have d electron, also you have f electron. Now as a result, what will happen, as these orbitals are having very poor shielding capacity, so the nucleus will have very high attraction for the outermost valence electrons, and as a result the size will be shrink. So the expected increase you will not get when you are moving down the group. So this is the actual reason. So individually they may be correct, but both A and R true, but R is not the correct reason. Okay. Energy difference between actual structure of compound and most stable resonating structure having least energy. This is called what? Now, if you simply apply a common sense, it is resonance energy, because in the statement itself it is mentioned most stable resonating structure. So this is actually as if a hint that resonance energy should be the closest option, right? Because it is talking about resonance energy. Actually, this is the correct option. But we will also see what are the other three. But okay, let me talk about the other three first, and then we will go to the details of resonance energy. So what is heat of hydrogenation? Heat of hydrogenation means, suppose you have unsaturation, simply take CC double bond. So when you add hydrogen, what happens? Now hydrogen is added, and as a result, double bond is gone. Now in this process, there is some energy released. So this amount of energy during the hydrogenation, that is actually called heat of hydrogenation, and it has direct relationship with the stability of the molecule which you are hydrogenating. It is basically alkene or alkyne. The more stable the molecule is, the less will be the heat of hydrogenation value. Okay, so that is heat of hydrogenation. It has nothing to do with resonating structure. Then heat of combustion is when you have any hydrocarbon, just take C2H6, ethane. So when you react it with oxygen, there is formation of CO2, there is formation of water. So this is a combustion reaction which is always exothermic. Some energy is released in this process. Hydrocarbon is completely reacting with oxygen, producing CO2 and H2O, and this process, combustion reaction, and the heat that is released, that is known as heat of combustion. So this is not our correct answer. And exchange energy is the amount of energy released when electrons with same spin swap position with degenerate orbitals. So suppose you have p orbital and there is 3 electrons present. Now suppose this is electron number 1, this is electron number 2, this is 3. Now 1 and 2, they can exchange their positions. 2 will go to the position of 1 and vice versa. The same thing you can also say between 1 and 3. So 1 is going towards the room of 3, 3 is going to the room of 1. So these are possible, and when this type of exchange is occurring, the energy which is released, because this process, this phenomena, it adds to stability of the system, and the energy that is released, that is known as exchange energy. So now we know what is heat of hydrogenation, heat of combustion, and exchange energy. But what is resonance energy? Though the definition is already given, but we will again try to understand. Here we have OCN minus NR. Now for this NR, you can see 3 resonating structures are there. and the middle one is the most stable, and the last one is the least stable. Now, details I am not going because that is not my purpose. Here we will try to understand that you have total 3 resonating structure, 1, 2, 3, and among these 2 is more stable, 3 is least stable. But when you consider the actual structure, you basically take the average. The average structure is the actual structure. Okay, so there is more stable structure, that is fine, but this is not the actual structure. The actual structure is average of 1, 2, 3, and the actual structure that is always having lesser energy than any of these structure. That is fine. So this is exchange energy. You can say it is the difference of the resonance hybrid structure, which is basically the actual structure. Whether you call it actual or overall resonance hybrid, that means average of all the structure. Actual or average, whatever you say, and the most stable canonical. So there will be some average structure, and the most stable is here, number 2. So this will always have lower energy and compared to any of the structure, even if it is more stable. So this energy difference, obviously it will be negative. That is known as resonating structure, which is mentioned here, that the energy difference between actual structure of the molecule and the most stable resonating structure. You can also write it like this, that the energy difference between resonance hybrid structure, which is nothing but the actual structure. The same thing is mentioned in the question. And the most stable resonating structure or canonical structure, that is resonance energy. So option 2 is the correct option. Which of the following is polar molecule? So to decide polarity, if you draw the molecule properly, this is basically alkene organic molecule. But look at this molecule, hydrogen and carbon, they are not having very large electronegativity difference, very close value, and that is why these bonds are not polar at all. And even if it is polar, the molecule overall is symmetric. Okay, and then if you consider CHCl3, it has tetrahedral structure, and if you consider all these CCl bond, so chlorine is obviously more electronegative, so all the dipole moments overall, if you see, it will be towards chlorine. So there will be some dipole moment because the bonds are not cancelling each other. So this should be the correct answer. But why not the other two we will consider as polar? Now CCl4, where all the, that is even this hydrogen is also replaced by Cl, so all the bonds are equivalent, so one will cancel each other, so overall there will be no dipole moment. And the same is also applicable for methane, because that is also tetrahedral. So correct option is CHCl. This is easier question compared to other questions. Consider the following statement. NF3 molecule has trigonal planar structure. Now for NF3, if you simply consider the steric number, nitrogen is having valence electron total 5. Monovalent atoms attached 3, and there is no charge overall. So it is giving you 4 steric number, that means it is tetrahedral. Now tetrahedral, one position there is lone pair. So this is the structure of the molecule. Actually it is without the lone pair, it will be pyramidal. So you cannot say this is trigonal planar. Trigonal planar you get when it is steric number 3, but that is not we are getting. So this cannot be true. Then bond length of nitrogen. Nitrogen is NN triple bond. Oxygen is double bond. So triple bond when present, that is high bond order, it will always be shorter. So this statement is basically correct statement. Then the third statement is saying, now if B is correct, either option 3 or option 4, any of these two, we have to choose. First two, not possible. Isoelectronic molecules or ions have identical bond order. Isoelectronic means what? Just take the example of CO, that is carbon monoxide, and Cn minus. Now these two are basically isoelectronic. How? For carbon, if you consider valence electron, that is total number of electrons, it will be 6, and for oxygen it is 8. So what you are getting? 14. Now again for the other species, same thing if you do, it is 6, 7 for nitrogen atomic number, but extra negative charge, again you are getting 14. So this is isoelectronic, And isoelectronic species, they always have identical bond order. Now, when we talk about bond order, it is the total number of electrons present in bonding orbital. I'm writing it as bonding orbital. Total number of electrons in anti-bonding orbitals divided by 2. Now, it is true that for isoelectronic molecules, bond order is same, but it is not necessary that they will always have same number of electrons in individually in bonding orbital and antibond. That is not necessary. But overall, the number will be such. That is, overall, the after subtraction, the number will be such. It will always be same for isoelectronic species. So that is why this is correct. So B and C, these two are correct. Last statement is obviously not correct. It is saying that dipole moment of H2S. H2S is this one, and H2O simply consider with water. Now in this case, in both cases there is lone pair, that is fine. But oxygen is more electronegative than hydrogen. Sulfur is also more electronegative. So in both cases, direction will be towards this side. But remember, the difference between S and H and the difference between O and H, obviously O is more electronegative than sulfur. So that is why the difference between O and H is more than the difference between S and H, and that is the reason dipole moment of water will be high, not H2S. This is false. And the last statement is the correct option. Okay. Statement 1, SO2 and H2O both possess V-shaped structure. So for SO2 also you can apply the same logic, that is a steric number. For sulfur it is 6. There is no monovalent atoms attached, and this is 0. So it will have 3 steric number. So that means it will be trigonal planar. There is lone pair present, but without lone pair, it will have a V type of shape. And the same is also true for water molecule without the lone pair. So this statement is correct. And it is then saying bond angle of SO2 is lesser than that of H2. Now, if you consider bond angle, that is this angle we are talking about. Now, these two are single bond. So, when it is single bond, there is basically 2 electrons like this present. Now, here the repulsion, and in this case, more number of electrons because you have double bond. So, this repulsion is very high. And when repulsion is high, the angle will increase. So the bond angle of SO2 cannot be lesser than H2. This is wrong. Statement 1 is correct, but not the second statement is correct. In which of the following processes the bond order increases? That means the first piece is, suppose this is initial, this is final. So the first piece is when you move from initial to final, bond order will increase and paramagnetic character will change to diamagnetic. Now this happens in which of these systems, that we have to understand. So first of all, we have to draw the molecular orbital diagram of all these species. So this is for oxygen, and for oxygen we know it is 2s2, 2p4. So 2p4 from 2 oxygens. So total number of electrons 4 plus 4, it will be 8. So if you place all these 8 electrons, sigma, pi, pi, pi star, sigma star. So this is O2 molecule which is neutral, and here if you consider paramagnetism, it is actually paramagnetic because of 2 electron, unpaired electron. But when it is converting to O2 plus, you are removing 1 electron. Obviously this high energy electron you will remove, but still there is 1 unpaired electron. So it is not changing from para to dia. This much information is enough. You don't have to calculate bond order. We have to solve the question first, because in the exam hall you will always there will be time management question is there, right? So it is not changing its paramagnetic character. This cannot be correct. What about O2 2 minus? That means 2 extra electrons are coming. Now when 2 extra electrons are coming, there will be some pairing. Now paramagnetic character is changing to diamagnetic. So in this case, if you consider the bond order, that you have to check, because based on paramagnetic diagram you cannot cancel the option. So for O2, here total number of bonding electron is 6 and here it is 2. 6 minus 2 is 4. But for O2 2 minus, it will be 6 minus 4. So 6 minus 2 is 4 and 6 minus 4 is 2. So from 4 divided by 2, it is 2, and 2 divided by 2, it is 1. So bond order is not increasing. This is not correct for O2 2 minus. So this is cancelled. This is cancelled. Now come to NO. For NO, here we have 3 electron. For nitrogen, 2p3 and 2p4 for oxygen. So 3 plus 4, total 7 electrons we have placed. Now see, there is unpaired electron. So this is first paramagnetic, and when you are removing one electron, it will be converted to diamagnetic. What about the bond order? Previously, if you see, total 6 electron, then 1 electron in anti-bonding divided by 2. But when you are removing this electron, you are converting to NO plus. Now it is 6 minus 0 by 2. So this is 3 and this is 2.5. So yes, bond order is increasing and this should be the correct option. But why the last option is not correct? In case of N2, this is P3, this is P3, total 6 electrons here. Now it is saying from paramagnetic character to diamagnetic, but it is not at all paramagnetic. So based on that, you can easily cancel it. Okay, it is not that for all the species each time you have to calculate bond order or paramagnetic. No, just apply some common sense. Just check whether one factor is it is obeying one factor. If it is not, obviously it is not correct. Just for nitrogen, the initial species is not paramagnetic. Then why the question arises paramagnetic character changing to diamagnetic, right? So third option should be the correct option. Now the next question. The bond order and magnetic property of acetylide are. So this molecular orbital diagram we have already seen. So the previous diagram will help us to understand this question also. Bond order and paramagnetic property of acetylide ion. Acetylide ion is simply think about acetylene. If you remove both hydrogen, there will be negative charge. Okay. So here bond order is 3, that we can easily understand. Total number of bonds 3. So in which of these species bond order 3, that you have to find. And also it is talking about magnetic property. That means whether it is paramagnetic or diamagnetic. So first think about the bond order, for which you have to take the diagram. So this is diagram of NO, but we need NO plus. That means this electron is not present. And here bond order, if you calculate, it is 6 minus 0 by 2, which is 3. That means it is matching. For NO plus, bond order is matching with acetylide. Now what about the other species? So we will just first try to understand that based on bond order whether we can cancel it or not. Now this is for O2, and here bond order is total 6 electron, total 2 electron. So 6 minus 2 divided by 2, it will be 4 by 2. So bond order will be 2. Okay, sorry, this is for not for neutral. It is for O2 plus and O2 2 minus. So when it is O2 plus, now there is only 1 electron. That means 6 minus 1 divided by 2, and this is 2.5 for O2 plus. Now this is not matching, so it will not be correct. Then what about O2 negative? O2 negative means now 6 minus 3. Now this is also not matching with bond order 3 of the given species. This is cancelled, this is cancelled. What about N2 plus? Now when it is N2 plus, that means these 2 electrons you are removing, total bonding electron is 4. So 4 by 2, this is giving you 2 bond order. So simply on the bond order, we can cancel all the 3 options and we will be left with NO plus. Now just check it. Why it is saying that magnetic property. So in this case, when it is NO plus, that means this electron is not present. This is basically diamagnetic, isn't it? Because we have all the paired electrons. Now, what about the acetylide? Acetylide means what? For each carbon, what we know, it is 2s2, 2p2. Just focus on the p. But as we have negative charge, so it will be as if p3 and p3 both side, right? So it is oxygen 2p4. There will be 1 electron. Sorry, this is a mistake. So for carbon, now both sides there will be total p3 p3. That means total 6 electrons. So its molecular orbital diagram, it will be just like NO. So all the 6 electrons, they will be in bonding, and that is the reason now you will have diamagnetic character for acetylide. So this is acetylide. For acetal it is diamagnetic, for NO plus also it is diamagnetic. But you don't need all this. Just based on bond order, you can simply choose NO plus without even considering this one, because the other three species are not having the same type of conditions. So this option will be the correct option. So we are at the end of the session. Thank you for listening.